amplifier, or op amp for short. It's basically a bunch of networks of solid-state devices that are built into an integrated circuit. So a lot of like transistors and stuff like that. So they always kind of build up different stages of amplifiers and differentiators and outputs. So here's our symbol for our schematic symbol, kind of a triangle, and then there's always going to be a minus sign there. That's our inverting input. Our positive sign is our non-inverting input, and then we have an output. And then they come in different IC packages, and then some of the IC packages can be 14 pins where they you can have 2 op amps on one integrated circuit. So I got our 741s, our little DIPs, DIPs, 8-pin op amps. So a real big thing when we're working with op amps, so there's a whole pile of
we got my schematic of it.
So on the data sheet, if I scroll down, here's what it looks like inside the op amp. And so you can kind of see there's a couple different types of op amps. There's one that's made with DJTs, and then there's also ones with FETs. So the ones that the 741 is, that one's configured with a bunch of transistors. So inside that chip is a network of the different transistors and resistors and stuff that are actually growing. They're growing with silicon crystals, and they're actually growing and stuff to form these junctions, our PNP junctions, and our resistance and stuff like that. So inside our op amp, we have a complex circuit. But the outside of it is just we just have to put in an output, and we get an we put in an input, and we get an output. And then we can do it by putting in either a feedback resistor and stuff like that, and that's how we kind of control our gain. So we're not really too concerned with, the circuitry inside there, other than we want to know that it's kind of come up into 3 different stages of how it comes out with the output. So that's what it looks like inside there. With the DJT type op amp, we still have a high input impedance, a low output impedance. But if we were to use like a FET, an op amp that was manufactured with using FET, then we'd have an extremely high input impedance and a low output impedance. And so that's one of some of the characteristics that when we're looking at op amps, we're kind of looking at what is an ideal op amp. So we're always kind of continually, when we're trying to analyze stuff, if we want to just kind of analyze how our devices are working, we kind of look at it that if I send in an input in here, if I'm coming from another circuit, the output of this circuit going into this op amp, the output of this circuit, what we want is, the ideal one is that the output of this circuit doesn't even see this circuit. That's our ideal situation, but we know that that's not really an ideal situation. There's going to be some kind of a input impedance on going into the op amp, and so the output of this circuit is going to see that. And just like on that common emitter amplifier, if I change my load, I'm actually changing my gain and changing my characteristics of what that common emitter amplifier is, depending on whether if I have a load on it or no load on it. So one of our characteristics that we like to look at when we're looking at an ideal op amp is that we have infinite input impedance. Then our next thing that we wanted our ideal op amp would be that it would have a very high voltage gain. Meaning that if I send in a signal in here, I send in an AC signal or some type of signal on here, that I can get as much gain out of this output without the distortion. No clipping or clamping going on and stuff like that. So that's our second item that we want to know on an ideal amplifier, is that we have very high voltage gain without causing any distortion on our output. Then our last characteristics of an ideal op amp is that we want to have a very low output impedance, meaning that it can drive as much current without having the IC either heat up, burn out, or malfunction something. So we have high input impedance going into the op amp, we have high voltage gain, and we have very low output impedance. So if I have a very low output impedance, so if I have another op amp and I'm coming out of my circuit, it won't be affected by the load. If I have a very low resistance on here, it doesn't affect what's going on there, because this is so low. Approximately what we like to do on the ideal op amp would be that it's 0 ohms. So it won't really have that voltage drop. If I have, for example, let's say if I have a load of, we'll just say 50 ohms, and my output impedance of my op amp itself has 50 ohms internally. If I put on a very large load, then we know that because of our Thevenin's circuits and stuff that we've done in the past, that if I have 50 ohms on my load, 50 ohms in my output impedance, then I'm going to drop half my voltage across the load, and then the other half of the voltage is going to be dropping across the op amp. So if I did have an output impedance of an ideal op amp, if I did have an output impedance of 0 ohms, then all my voltage would be dropping across my load. I wouldn't be getting any internal drops across that output. So that's what we're really kind of looking at is, my high input impedance, high voltage gain, and a very low output impedance. All right, let's see. So here's our, on 847 there on the bottom of the page there, here's kind of the block diagram of our op amp. We have 3 different stages. We have our differential amplifier. That's our input stage. That's going to have the high input impedance. So we're going to be bringing in our signals into here. It's going to be taking a look at the different signals. It's going to take that signal, do the comparison of these two, bring it into our voltage amplifier. That's where we're going to amplify it. It either can be uncontrolled or controlled, either an open loop or a closed loop type amplifier. It's going to amplify the signal, and then it's going to go into what we call a push-pull amplifier. And then this amplifier here, this push-pull amplifier output stage, this is where we have our very low output impedance. So this is going to have very, very high input impedance. It's going to have our voltage gain, and then our output stage, which is going to have our low output impedance to drive it. This is the part that's going to be able to handle the different currents and stuff. So we could have something that can't handle much current. It's going to look at the signals, it's going to amplify it, and then it's going to take that signal and convert it so that we can drive large amounts of current. And when I'm talking about large amounts, like on the 741 op amp, we're only going to be capable of 20 milliamps. And this really actually, this one kind of caught me off guard. I didn't realize that it was only at 20 milliamps. I've never looked at the data sheets on the 741, but I know when we were working on the curve tracer for the DJTs and stuff, we were getting some weird characteristics curves because of our data on our transistors were so high that it was really trying to drive a lot more current than what was capable of our 741. And we found out that after 20 milliamps of current trying to go through our curve tracer, that the 741 actually ended up starting to die out. It started dropping the voltage. It was trying to increase the current, but the voltage was dropping as it was going because of the output impedance of it. So then when we're looking at these types of signals, we can have, when we're looking at this differential amplifier on this first stage, what we can have is we can have a couple different ways, and this is how like the MIDAC works. So this would be our, so for example, this would be our +0 and our -0. Those are our inputs going into the MIDAC. And we also have our other analog input, which is our +1 and our -1. So we can have two different types of inputs in here, and when we're out in the industry, we deal with these types of inputs and how we want to maintain it, or how we're bringing them in. So, for example, if we're going into like a servo drive or something like that, when we're trying to control the speed of our servo or our AC motor, we have to determine whether if we want a differential input or a single-ended input. So if I want a single-ended input, basically one of these pins will be grounded, and then my other signal here will be some kind of a variable power supply, depending on what we're coming out of. It might be coming out of another op amp or coming out of something else. And what it's going to do is this voltage might vary from 0 to 10 volts. And as I vary that voltage, it's just all it's doing is it's comparing it with our inverting pin. And so this thing is going to be looking at the difference between these two channels. So inside here, this thing is only going to see it from 0 to 10 volts. And then it's going to go into a voltage amplifier, depending on what type of circuitry we have in our servo. It might be just like our voltage follower, just the exact same type of configuration that we have on our MIDAC coming out of our analog output for our variable power supply, and then go into the rest of the system. So these are what we call the single-ended input, just comparing it with something that's at 0 volts. So if this thing goes from 0 to 10 volts, that's the differential input stage. It's going to go from 0 to 10 volts. The other type of input that we can be looking at is what we call a differential input. That's where we might be comparing two different signals, and it's going to be taking the difference of those two. So for example, if this one's set at +5 volts, and this one's set at, we'll just say +4 volts, what it's going to do is it's going to take a look at the two signals. Instead of seeing the 5 volts going into our op amp, what it's going to do is it's going to take the difference between these two signals. It's going to look at the +5 volts and the +4 volts, look at the difference between those, and it's going to give us a +1 volt. This is what we call our differential type input. So if we're trying to compare two different signals and stuff, we're going to take the comparison of those two signals, it's going to take the difference of those two signals, and then send that into our voltage amplifier, and then over to our push volts. So those are kind of our two main types of signals that we're looking at, and that's how we're using the MIDAC. So a good example of the MIDAC, if we're using our oscilloscope, if I'm using it as a single-ended input, I'd have my analog input, my +0, channel 0 there, and then my -0 would be going to my reference point. So what it's doing is it's referencing our plus and minus 0 volts, and it's just taking the difference between these two signals. And then it's going to give us, so on channel 0 then, it's going to just measure our source voltage, our AC signal of our source voltage. If I wanted to know just the voltage drop across R1, then what I can do is I can do the differential type input, and this is where I would go ahead and I would hook up, and I'll do the other channel. This would be +1, and this would be my -1. these two here are going to be our differential inputs. So what it's going to do is it's going to look at what the voltage is. Now it's still going to be with respect to ground. Okay, we're still going to have our reference point. This is still going to be our ground. But what it's going to do is it's going to look at what, referencing it from our reference point, even though we don't have it actually hooked up to our reference point, it's still going to be using our reference point. It's going to look at what that voltage is at our +1, and then it's going to take a look at our -1, and it's going to look at that voltage, what I get for a voltage at that 2, and it's going to take the difference of those two voltages, and then we would end up with a voltage drop of VR2. So channel 1 is going to be our differential type input, and then channel 0 would be what we would call our single-ended input. We automatically just go ahead. But like I said, our reference point is always important to us. That's where it's referenced. It's still referencing those points, but it's really where are we putting the inputs across our components. And so when we're out in the industry, you'll hear a lot about either you got to hook it up as a single-ended input or a differential input. And that's the difference between those two. Any questions on that? Does it all make sense?
So what you just explained, Kurt, that's like the malfunction on the scope, right? It's the same concept.
What's that?
That's like the malfunction on the scope, the same
Yeah, that would be like the math function on the scope. Yep, that would be actually, because it is really a math function. It's just taking our +1 minus our -1, and then it would give us the difference between those two channels. So it is just a math function. It's just channel 1 minus our +1 minus our -1. Yep. So it's basically really just it's basically, if we really look at it, it's just, we're really adding them together. So VR2 is equal to +1 minus 1. So we take the difference between those two channels. Yep. So it's just algebraically, really it's algebraically adding it up. All right, let's see. All right. All right, so I'm gonna let you do I'll let you read on that, the differential amplifier using those two BJTs. There is a lab on that, but I just skipped that lab. We're really concerned about how to use the op amp and stuff like that. But that is good reading, and if you did want to do that lab 36, I think it is, or 37, lab 37, if you want to do that as extra credit, you can do that one as extra credit. But make sure that we get knowing how to use op amps and stuff like that, I kind of just take that one off. All right, then we'll come back on page 851 there on our common mode. But let's take a look at our first worksheet so we can kind of see how the op amp actually functions, and then we'll come back and look at that common mode once we understand the theory of how the op amp works. So we're going to look at the open loop comparators. See if I can, what I'm looking for is what we call our, so if we're looking at an open loop, what I'm looking for, what's that?